Yeah, good morning, good afternoon, good evening to you wherever you are in the world. I'd like to welcome you to EMinar Wednesday, and today I'm giving a talk on North American Central Plains conductivity anomaly. So first of all, though, to remind you to go onto the EMinars page where you'll find videos of prior EMinars and presentations of prior EMinars, and also you can register for upcoming ones. And you are on a Zoom webinar, and so you can change your audio settings, you can send a message, you can raise your hand if you want to speak at the end, or you can send a Q&A. And I've got the Q&A window open, and I'll try and glance at it, and if it's a short question, I'll answer it on the fly, otherwise I'll answer it at the end of the webinar. So today we're going to talk about the North American Central Plains anomaly and 50 odd years of study of it. And I think the story is a fabulous one, actually. So just very quickly about me, I think most of you know that I've been studying and developing MT since what I call the dark ages, 1974. I've been doing this 47 years, and I've applied MT at all sorts of problems at different sorts of scales. I have over 200 papers published and 15,000 citations. I took early retirement from academia, but continue research with colleagues worldwide, and I'm consulting. I've started a consultancy. So, anatomy of an anomaly, North American Central Plains conductivity anomaly, from its initial discovery to understanding, and from the craton to grain scale. So, we're going to start way back with this device. This is the first device that was used to detect the NACP. And it's the so-called Gough-Reitzel magnetometer. And this is the paper from Ian Gough and Reitzel, published in 1967. And these magnetometers were almost 6 foot tall. And there were 3 suspended magnets suspended on torsion wires. And the movement of them, and the magnets had little mirrors on, and the movement of them was reflected back to a camera. And I actually used these in Scotland when I first went to Edinburgh. And then we used them again in Scandinavia, designed by Ian. Very quickly, want to mention, many of you may not be aware of Ian Gough because he's been dead a decade now. But he was an absolutely excellent, what I would call a Renaissance scientist. And he had huge amount of impact in a number of fields. He invented the hammer seismograph in 1964. He worked in geothermal studies, he worked in gravity and isostasy. He invented the spinner magnetometer that's ubiquitous in paleomagnetism. He invented the Gough-Reitzel magnetometer. And then he worked also in stress and rheology, and his most referenced work is actually on northeast southwest compressive stress in Alberta from oil wells. And he brought all his understanding together in this Nature paper in 1986 that correlated seismic reflectors, conductivity, water and stress in the continental crust. A lovely paper, and I encourage you to read it. So Ian, he had a lot of administrative impact as well. He was the president of IAGA, and he was the champion of non-seismic geophysics in lithoprobe. And we in Canada, Martin Unsworth, in Ferguson, the rest of us, we've got Ian to thank because he demanded that MT be a very strong component of lithoprobe. His papers are still being referenced today, something like 40, 50, 60 citations a year. And I'm very fortunate that his last science paper he wrote together with me on images of the Southern Cordillera. Upon retirement, he turned to writing poetry, and he often said that it was harder to get his poems published than his scientific papers. I think of him as the last of an age. He was a true Renaissance scientist, and he was a true gentleman. Anyway, so what did he do with his magnetometers? And this was the first array where he installed them in Western United States, and you can see the stations here. From the Basin and Range all the way over to Nebraska, not quite up to this is at 45 degrees, so the US-Canada border is much further north than this. And you can see the first paper published on this work. This was a 67 array paper published in 1970. And one of the people who worked on acquiring the data was somebody called D.W. Oldenburg. And Doug went on actually to look at various aspects of these arrays, the source field effects actually. What Ian found when in those days, that these were magnetometers, they were all recording at the same time. So you had synoptic observations, and then they could compute for various events. They picked events on the films and digitize the events and digitize them. Something that I had to do when I went to Alberta in '74. And he hand digitized the events, and then they processed them, Fourier transformed them, and they looked at the amplitudes in various components. And these are the amplitudes in the horizontal components at 30 minutes and at almost 90 minutes, 89 minutes. And what you can see is a very strong concentration of these lines, effectively current, mapping current here. There's very strong concentration in the northeast corner in northern part of Nevada. And this became known jokingly as Gough's law, because it didn't matter where Ian put his array, the anomalies were always in the corner of the array. So a very, very strong anomaly in these, and that these long periods imply that the anomaly is deep. So then they went and did a second array, which crossed over into Canada now, as you can see, across the Canadian and the US border. And this work was published in a couple of papers, Adrian, Camfield, Ian Gough and Porath, and Porath, Gough and Camfield. And of course, when they looked at these, they found that the big anomaly was right at the edge of the array. And here we're looking at periods of 102 seconds. So very long periods, so a very deep conductor. And this very strong concentration of lines here means a very strong concentration of current. And these were spatially located close to an area in the Dakotas called the Black Hills of South Dakota. And these actually, these concentrations existed to very long periods. Here we are, something that Adrian Camfield looked at. As on the left side, you see these field lines from active days, so periods of 25, 47, and 100 minutes. And on the right side, they took some very quiet days, 5 very quiet days, and so looked at the Fourier transforms of those, and you find that this concentration of current exists down to 12 hours. You kind of lose it at daily variation, but whatever is causing this concentration of current is a very, very long period, 12 hours period. So they then had a look at a profile, and here I'm showing you a profile, and they computed the anomalous horizontal variation compared to the normal horizontal variation. This is D, which is basically east-west field. And they computed the ratio of the vertical field to the normal horizontal field. So this isn't Tipper as we know it, which is vertical to horizontal. This is vertical to normal horizontal field. And the normal horizontal field was at the edges of each profile. And as you can see, these very strong variations right across that anomaly. Very strong vertical field response. Look at this. You've got a vertical field response 2.5 times the normal horizontal magnetic field. And this was thought impossible by physics. And so they invoked something called current channeling. They said, this can't happen. It must be current channeling. So I looked at this some years later. And what I did was I took their Z over D, which is these data here, this crossover here, and I did a Fourier transform of it. Now we've known since 1954, a paper published by Kurtz, the so-called Kurtz operator, that the vertical and horizontal fields are related by the Hilbert transform. We know this in MT from D plus and Rho plus, but it's exactly the same in geomagnetism, that the vertical and horizontal fields are related both in frequency and in space. And here we're looking at a space variation. And so I took the vertical field, did a Fourier transform, and that's this dashed dotted line, and you can see that it fits the data very well, fits the observations very well. So I then proposed a very extreme model. Gough thought that you had to invoke this spectra of current channeling to explain the data, but I proposed a very extreme model, completely non-geological, but just to show that you could fit the data with a 2D model. And this extreme model is a thick conductor, 2 kilometers thick in the upper crust of 0.1 Siemens per meter. So it's completely unfeasible geologically, but it does fit the data to first order. So the next study that they did, they realized they really had to understand what was going on. They then moved over further to the east, just like US Array did footprints. They did kind of the same thing with these geomagnetic depth sounding array, GDS arrays. And they did a footprint in the Dakotas here, around Williston Basin, and then up into Canada. This line here that you can see, that line is the limit of exposed rock. So anything to the west and south of that line, you've got sedimentary cover. And the Williston Basin is 3 kilometers thick of very conducting sediments before you get to basement. And so you've got thick sedimentary cover, so you don't see the exposed rocks, but up to the north and east of this line, you've got exposed rocks of the Superior province and what was at the time called the Churchill province. And so the Remi Labi from Nigeria had joined Ian in Edmonton for his PhD. And Remi was the lead author publishing this work. And as you can see, they used for the first time the title North American Central Plains Conductivity Anomaly, or NACP. And what they found was that here's these Fourier transform maps again at 30 minutes. And particularly in the phase of the vertical field, they showed this very strong current concentration coming up on these are the Dakotas, so North Dakota, South Dakota, so on the western edges of the Dakotas, coming into Canada. They then computed the anomalous or residual maps, and the way they did that was to take the components at the end stations and subtract them off the Fourier components along the profile, and so they're getting the residual coefficients, cosine coefficients. And this shows quite well that these two periods, 68 seconds and 170 seconds, this very strong concentration of current coming from the Dakotas into Canada. On the basis of this, they proposed that there was a conductivity anomaly, basically coming from the Black Hills of South Dakota right up through the Williston Basin into Canada, into the northern part of Canada. And this was the so-called, they call this the North American Central Plains Conductivity Anomaly, NACP. Now, on the basis of this, and you must remember this was the 1970s, not a lot, almost nothing was known about the geology beneath these thick sedimentary sequences. There had not been a lot of boreholes to depth. And so very little was known. We knew that up here, and papers had been published, particularly by Gibbon Thomas, proposing that there was a tectonic boundary, that this so-called Churchill province represented an orogenic boundary between the Superior province to the east and other provinces to the west. So you had a tectonic plate boundary there. And so on the basis of that, Adrian, Camfield and Ian Gough published this paper in Canadian Journal of Sciences in 1977, suggesting that this North American Central Plains anomaly was a marker of a Proterozoic continental collision zone, or a geosuture beneath the Great Plains. And this, I think, is phenomenal because nobody had thought of this before. It was the first paper to published to suggest that a major continental scale boundary existed all the way from northern Canada beneath the Williston Basin and down into the Dakotas and south. They went on further to propose that the cause of the NACP is graphite. And the reason they came up with this Proterozoic age is that they correlated the North American, their image of the location of the anomaly with Proterozoic structures at the southern end. And here you have these Proterozoic structures, the Black Hills, the Hartville Arch, the Whalen Fault. These are all Proterozoic in age. And they also noted that graphite occurs in some of these exposed terrains. And they correlated it with Proterozoic structures at the northern end, the Needle Falls shear zone, as part of the what's called the Wollaston domain. And they'd been talking to somebody from Saskatchewan who told them that a lot of the linear belts are due to graphite units. And so they had some sort of Proterozoic graphite units at the northern end and Proterozoic graphite units at the southern end. And that led their interpretation to this idea that there's a continental collision, and what we're seeing is some sort of long structure related to graphite emplacement during collision. But they also went on to suggest that a lot of structures seen in the Phanerozoic sediments is this structure called the Nemo Estes Trend, which is in the Williston Basin. And this is a Phanerozoic structure within the Williston Basin. They went on to suggest that Proterozoic structures in the basement controlled the location of Phanerozoic structures in the basin. And we'll come back to that. So we now know, and we've jumped ahead quite a few years, because here this is what we know now. We have the Superior Craton, the Wyoming Craton, the Hearne Rae Cratons, and continental margins in green. And here we have the Trans-Hudson Orogen, the known Paleoproterozoic orogenic belt that's been mapped geologically at the surface, and also drill holes through the sediments into basement. And so this is quite well established now. And here you can see this red line, which is the North American Central Plains anomaly from GDS. I should say just GDS at this point. So in order to try and track it further north, Hander and Camfield did some work in the early 80s where they put in a profile of 7 magnetometer sites right across this Needle Falls shear zone. So here we are now in northern Canada on the exposed rocks. This is the suggested extension of the NACP, and here you can see in these black blobs is the Alabi sites. And here you can see the locations of their sites, and the locations on the transect had been on the presumption that they were tracking this thing called the Needle Falls shear zone. But when they looked at the data, and I'm now showing you induction arrows at various periods from 2 minutes to 40 minutes, their expected trace of the NACP was going to be between stations 3 and 4. But that's not what they found. They found a very strong reversal in induction vectors between stations 5 and 7. With station 6, I don't know whether it wasn't working at the time, but there's no vectors shown. Perhaps there's no vectors because the station's on top of the conductor. And here on the bottom left here, you can see their model. They're very cartoon sketch of their model, a rather rudimentary model to explain the data. And they had a conductor of 10 ohm meters from 5 kilometers down to 30 kilometers. So a crustal conductor that would explain these induction arrows. And this crustal conductor is in this domain called the Lagrange domain, and we'll come up against the Lagrange domain more and more as we go through the talk. So now they've extended this, the Hander and Camfield works up here, and we can say, okay, we can extend this NACP right through. And of course, none of this was known at the time. I'm showing you this on top of what we now know. And subsequently, Jagdish Gupta was doing some work on a bunch of stations that were laid out for the IMS, the International Magnetospheric Study. And this was a north-south line of stations going up through the western side of Hudson Bay. And he noted a conductor that, and I'll show you in a minute, the conductor between two stations, this one called GIM and this one called BKC. Now, those of you from Canada might know GIM because that's where the Gimli glider landed. It's the 727, was it? They forgot to put enough fuel in. It ran out of fuel and the pilot had to glide down into Gimli. And so they, because of the nature of the known geology at the time, they said, okay, this conductor that they're finding here is a long strike from this Larange conductor, this LR here, the Larange belt, Larange Larder Lake belt. They said it's the same conductor, right? And so they extended this NACP now all the way around, and we can see that it lies wholly within the Trans-Hudson Orogen. And their particular model of the data, forward model of the data, again, has got this crustal conductor from about 5 kilometers down to about 40 kilometers of 25 ohm meters. So a conductance, vertical integrated conductance of order 1400 Siemens. The next thing that happened in the early 80s, the Pan-Canadian Oil Company was very interested in the suggestion that Proterozoic structures in the basement could control Phanerozoic structures in the sediments. And so they contracted Phoenix Geophysics to do a profile of sites in 1984 across the location of the NACP from the GDS studies. And these crosses were the locations of the GDS data. But what they found, and I'll show you this in a minute, was that in fact the NACP isn't here, it's further over to the east. So they did a second profile in 1985. So a total of 35 sites along this east-west profile, the ones to the west from 1984 and the ones to the east from 1985. And when I got these data, I was asked to look at these data by Pan-Canadian Oil Company. And when the first thing I did was plot a pseudosection, a phase pseudosection, and these are the TE mode phase pseudosection. And you can see that this is the location here of the NACP as proposed from those very widely separated GDS sites. But we get a phase maximum that occurs further to the east. In fact, very close to this town here called Macomb, at almost exactly 103 degrees west of London. And I published that paper in '86. And here you can see the phase is at 100 seconds. That the GDS location of the NACP was over here, whereas the MT would give a very strong phase response and locate it further to the east at Macomb. And we also noted a second anomaly that we labeled Toby because it was related along strike to the Thompson nickel belt. And I won't be talking about this anomaly in this talk. I'm going to focus on the NACP. So here in this dash is the NACP from GDS. And here, this line here is where it will be placed based on the MT. So we just shifted it 1 degree, so 75 kilometers to the east. Now, an interesting thing about the data is that the westernmost sites, this shows some representative westernmost sites, and it's got both the TE and the TM mode shown here, and they're completely on top of each other. So you have very isotropic structures. And then when you're right on top of the NACP, what you find is that the TM mode looks like it did before, but you've got a very strong TE mode response. And you can see it in phases as well as in apparent stabilities. And then you move slightly further east and you're back to almost isotropic behavior. And then you move east again on top of this Toby anomaly that we won't be talking about. And you get, again, very anisotropic behavior with the TE mode showing a conductor, whereas the TM mode doesn't. And then you go east of that, and the easternmost sites on the profile again show very isotropic behavior. And so you've got this very strange behavior along this profile of isotropic, anisotropic, isotropic, anisotropic, and isotropic. And so looking at all these three together, particularly for around on either side of the NACP, you can see the differences that when you're on top of the NACP, you've got very strong TE mode, currents traveling up and down the conductor, very strongly affecting the stations. Above, but currents traveling east-west are hardly affecting it. They do affect it, and I'll show you shortly, in a very minimal sense. And when we look at the B polarization or TM phase, what we find is that, in fact, there is a very faint, it's only a couple of degrees, but a very faint phase low associated with this NACP, just here. And we have to keep this in mind, and I'll tell you why in a minute. So if you just do 1D Occam inversions, and this is what you get. Here is this NACP, and I think the 1D has given us a very good image of the top of this structure, whether it extends to depth, we're going to explore. And over on the east here is this Toby anomaly, Thomson-Nickelbelt anomaly. At that time, I had forward modeling as available to me, so I came up with two forward models, one of separated conductors and one which I thought of as connected conductors, but as John Booker pointed out to me, in fact, there was no connection because only these conductors here are connected. Because these conductors are not connected, they're touching at the edges, but there's no flow through of east-west current. So in fact, both of these really represent the same thing, are disconnected conductors. So I sent those data around the community and saying, hey, can you all do 2D inversion of these data? And this is the CoProd2 study. And that paper was published in 92, I think it was. And these are my models up here. And you can see a number of people did inversions using different codes. This is codes available in the early 90s, 2D inversion codes, including even a Monte Carlo code from Mark Everett and Adam Schultz. What you can see is that essentially the types of models, they fall into two classic types. One is where you've got smallest gradient, so you've got the least number of blocks. And the other is, one is smallest number of blocks, so it's a minimum structure in that sense, quite strong gradients between blocks, but minimum number of blocks. And the other is smallest gradient, the smoothest inversion, as you might say. These both are in some sense smooth because this is the lowest number of blocks and this is the lowest gradient. So they're both minimum structure in their own way. And according to the RMS misfit, they both fit equally well. So just to remind you about this minimum here in the TM mode, right? This couple of degrees minimum. Let's see how well those models do. And I've shown you here a couple of models. One is the Uchida model as representative of those discrete conductors, and the Agarwal model as representative of the big blocks. And here's the data at 57 seconds. And you can see that this is the TM mode data now. The TM mode data shows this faint minimum. And the Uchida model fits that minimum, whereas the Agarwal model, which is this straight line, misses it. And so all of these models describe current flow along the NACP, but what the Uchida model is able to do is fit the charges on the boundaries from the TM mode better than the big block models. And this means that the structures have to be disconnected. So I won't get into this, but that NACP images that we've been coming out with were used by the seismologists in terms of, this is Doug Nelson and colleagues, in terms of a reinterpretation of the geology. This is the conventional view of what was happening, that you had the Superior Province to the east, Wyoming Province to the west, and you had this subduction zone, collision zone that was westward dipping. And you had the internides of the Trans-Hudson Orogen. And their paper, sorry, I don't have the paper on here. I should have, Nelson et al. They they suggested for the first time that from their seismic data that they were seeing reflectors going both sides, and that there was an Archean microcontinent, and that the Nacp seemed to sit right on top of this Archean microcontinent. So the next thing that happened was that Jim Craven and I went and did some work in Saskatchewan along two profiles that we call here M and S. We've just been looking at this S profile, sorry, the two profiles there, M and N. And then when we look at those in detail though, and here's the data now, the E polarization data and the B polarization data, and looking in particular at the E polarization or the TE mode data, what you'll see is very strong phases at 10 to 1,000 seconds on the N line, and very strong phases on the S line that we can associate with the Nacp, but much weaker phases on the M line. And so we're suggesting that perhaps the Nacp is not a continuous structure, that it has a break at around where we just happen to put our M line. And so this is how we would represent it based on the work to date. And then subsequently, John Booker and I and Nong Wu, his student, did some measurements in what we call the North Dakota or NOD. We did 3 profiles of long period measurements using the GSC limb system. And the models from that, here on the top is the model from that S line, that Pan-Canadian line. And here's the models produced by Nong Wu of the other 3 profiles. And you can see that all of them show exactly the same blobby behavior. And I'm going to try and convince you that this blobby behavior is numerical expressions of anisotropy. Now, fortunately, we then started to do lithoprobe work, and the advantage of lithoprobe work was it was done right along the boundary of exposed rocks. And so we could relate what we saw to the subsurface. And this is the lithoprobe main profile, east-west Trans-Hudson main profile. And the yellow crosses on it are the stations that we acquired in 1962. And then in 64, we acquired some more stations along this profile called S2B. Now, the seismic reflection along this long profile was consistent with what had been found much further south at the US-Canadian border by Doug Nelson and others. And they suggested, in fact, that there was this inferred Archean cratonic remnant, which they called a Sask craton, that lay beneath the internides of the Trans-Hudson Orogen, and it was essentially hidden by all these various rock units that lay above it. And here to the left here is this Larange domain that we're going to talk about shortly. Well, Ian Ferguson and I and Kevin Stevens published a model based on the whole of that profile. And here you can see the Larange domain and these dipping structures that lie in the Larange domain right above this, this reflector, which is called the guncoat thrust, which separates out the Larange domain from the Glenny domain. Another conductor was imaged by in this model, but later modeling we're going to show, we're going to push this a bit deeper. And so this 2D model has got this dipping strata and this lower crustal conductor. Well, here we are now. I'm going to focus particularly on the western part of this line where the Larange belt is and the rotten stone. And here's the Needle Falls shear zone. If you remember, that was the one that way back Camfield and Gough and Alabi had suggested was the continuation of the Nacp. But in fact, we now can relate it to the Larange belt here. And so very quickly, we did strike analysis and showed the strike was pretty consistent, just east of north. And these are the TE and TM mode or repolarization, bipolarization data. And you can see a very, very strong phase response from 100 Hertz down to about 1 Hertz in the TE mode, and a lack of phase response in the TM mode. Now, these are higher frequencies than we talked about beneath the sediments because the anomaly is close to surface. And this is the model that I produced from those data compared to the seismic data. Here you can see seismic reflection on top of it. Here's the guncoat thrust that defines this boundary between the Orange Belt and units to the east. Here's the Needle Falls shear zone. What I was able to show is that the North American Central Plains conductive structures lie wholly within the Orange Belt and dip to the west, consistent with this guncoat thrust, and in fact are stopped right at the Needle Falls shear zone. Now, if I take these sites here and I invert only the very high frequencies, I get this very strange model of intermittent repeated conductors separated by resistors. And so we're going to come back to this. Subsequently, in 1994, we did this profile along MT work along profile X, and Xavi Garcia and I worked on that data, and we published that. And here you can see a big conductor in the Orange Belt, and that this profile X is fairly close to the Hearne and Camfield profile. And here's Hearne and Camfield's model up to the right. And you can see that these two are very reminiscent in terms of what was found. Well, we can extend the Trans-Hudson Orogen to the east. And this is a geological map of the whole of northeastern Canada showing the Trans-Hudson Orogen and its potential extension over to the eastern part in what's called the Fox Zone. And here's Baffin Island. So we did projects on Baffin Island, 2002, 2003. And my student at the time, Shane Evans, and Jessica Spratt, and John Katsubi, who did the physical property work. We published this model. North is now to the right, south to the left. And here you can find North American Central Plains, and exactly like we saw way over in on the other side of Hudson Bay, this very blobby structures that we can associate with the Trans-Hudson Orogen. Now we can even potentially extend this much, much further to the east. And I suggested this in a paper I wrote in '93, and I modified a diagram from Condi in 1990 to show the pan-Scandamerican orogenic belt of the Trans-Hudson Orogen has potentially got correlatives in this particular origin here, Nassau-Quidian belt of Greenland and the Svekofenian belt. And so we have potentially this, by far the longest orogenic belt in the world, and we know that we have conductors associated with the Svekofenian. And we map these conductors on Baffin Island, and we've mapped these conductors in the Trans-Hudson all the way down to its southern end. And so we've got continuity of conductors along this belt, which implies continuity of orogenic processes. Now, I want to look in detail at this particular area where we map the NACP right within the Orange Belt. So here's the Orange Belt, and the NACP on surface, this located by these stations, lies wholly within the boundaries of the Orange Belt. So we went out and collected some rocks. We went into the field. When I say we, it was John Katsubi that did it. Went into the field and collected rocks exactly where I told him to collect the rocks. And he was guided by this very old aeromagnetic airborne EM map from the 70s. I don't know whether there's newer data, but this was the map that guided us at the time. And this is a compilation of data from the 1970s that showed these long linear conductors. And if we focus in on this particular one here, you can see these long linear conductors within these areas that were flown. And this area is called Sulfide Lake. Now that's kind of going to give the story away. This is Sulfide Lake. And so we went and collected the samples all around these lineaments, and here you can see Sulfide Lake, this sample 94-7. And when we look at these in detail, this is what John found. We are quite amazed. He did the rock property measurements. These cubes are about 1 centimeter on a side. And when he took cubes, and this is a cartoon of the rock, first of all, observations of the rock show that the sulfides were in the hinges of folds. And when he measured the conductivity, he found that there was very high anisotropy. And sorry, this square here should be ohm, of course. So very conducting along strike of the fold hinges, but much more resistive across strike. And you had both concentrated sulfides and disseminated sulfides. And so our interpretation was that the sulfides during deposition and compression during orogenesis, the sulfides have migrated to the fold hinges, and the sulfide grains, these are pyrite grains, the grains are connected along strike, but not across strike. And so then we did a SEM scan of our samples, and we found exactly that. So this is an SEM scan across strike, and here you can see these little yellow dots, these are sulfide grains, and as you can see, they're not connected. And so you've got very high resistivity, relatively high resistivity, hundreds of ohm meters. But when we cut them along strike, we find these sulfides are connected by these black things, these black stringers. And these are pyrite stringers, iron oxide stringers. And so we've got connectivity along strike, but no connectivity across strike. And if we sample up to try and get to a hand sample scale for these different subsamples, we can get anisotropies of the order of 1,000 to 1, depending on where we are. And so this is the story now. We've got these sulfides in fold hinges that have been compressed during convergence on the western side of the Trans-Hudson Orogen, and they've been pushed down deep into the section, down to about 25 kilometers. They've ended at the needle fall shear zone, and these sulfides are connected along strike, but not connected across strike. Now, what's the tectonic implications of this model? And here on the top is the current tectonic, here this page shows you that the believed tectonic model was that initial subduction polarity was to the east in modern day coordinates. And then there was a flip at around 1855 to westward directed subduction. And then there was convergence from 1830 to 1790. And so you had initial subduction and Larange sediments initially subducted to the east. Then you had subduction to the west. Now look where these Larange sediments would end up with this model. They don't end up in the right place. And so I proposed, based on my results, that in fact this is not correct, that we had continuous westward subduction to get the Larange sediments deep into the crust where they are today. And so pulling this all together, this is something that Juan Oledo, when he was with me in the GSC, and I and Ian Ferguson did, we pulled everything together. And here you can see some maps, various depths. These are approximate imaging maps. They're not models. And you can see how this dashed line is the NACP, this orange color is conductor, but also in these green colors, you can see this outline of a more resistive domain. And this is the domain that we associate with this craton, the Sask craton. So we've mapped the Sask craton down to deep crustal depths, and we've mapped the NACP. And Juanjo went through the process of forward modeling all of those profiles, and here you can see the 2D models along the whole profile. So here's the known extent now of the NACP, lying with it, with all of the data that we have. How do we explain this in terms of an evolutionary model? So initially we had deposition of the metasediments and the syngenetic sulfides between the Larange arc and the Wyoming Hearne craton. Subsequently, we had compression and folding of the metasediments. and migration of the sulfides. Then we had sinistral, see the sinistral break here along the so-called Taberner Fault as a part of the, which broke up the Nacp. I told you we had this break in the Nacp. And so this is the end of the origin, the present day location. So 2D inversion of the MT data on the end, on the western end of this profile shows these conductors associated with the Larange belt. Now, what other evidence do we have? Well, we have lots of evidence. If you look at mineral showings along the Larange belt, we have unfortunately, there's no world-class deposits, but there's a lot of mineral prospects and mineral showings. And here you can see all the different mineral showings. Gold is in gold, copper, zinc, and copper, nickel, PGEs, all of them lying along, in sulfides lying along the Larange domain. And this is published by the Resource Map of Saskatchewan, which for some reason also has a Chinese title. And more recently, the Northern Miner suggested that there's a lot of riches that lie beneath the Canadian prairies. Well, I think we've mapped them. I think we've mapped, because of this intimate relationship between the Nacp and these sulfides, I think we've mapped where those riches lie. There's a very recent story published earlier this year by Paul Bedrosian and Carol Finn, and they've taken the NOD data as well as some new US array data, and this is their image from 30 kilometers showing the Nacp, and they focus on what they call the STHO, the Southern Trans-Hudson Orogen, and they have their own tectonic story, and I won't go into this. I'm putting it here for you to just to make it known, and you can read the paper. But I have a new story. And this new story is anisotropy. I've been telling you all along that I think this is anisotropic. So let's try and model it with an isotropic code. And I'm using the code here written by Randy Mackey. And what Randy does is, in order to make the problem tractable, he assumes that the anisotropy strike direction is the same as geoelectric strike direction. And so when you do that, Maxwell's equations separate into the two modes as it does in isotropic conductivity. You have the TE and TM mode. In an anisotropic case with your axes of anisotropy aligned with the strike direction, then again you get separation of two modes. In one mode, you've got the conductivity along strike, sigma XX, and in the other mode, the TM mode, if you like, you've got the conductivity across strike and the vertical conductivity. And so you can see how anisotropic inversion, let's see how anisotropic inversion fits these data. So here's the data along that profile, this line L. They're just like the coprod data. Here we have the TE resistivity in phase, and here we have the TM resistivity in phase. And you can see we have this TE phase, this very strong anomaly that's not present in the TM phase. And this is the signature of the Nacp, this very strong phase anomaly. Let's do it. First of all, we'll do independent inversions, right? So on the top, we have a TE only inversion. And then the top, on the bottom, we have a TM only inversion. And the misfits of the TE only is 2, and of the TM only is 2.7, assuming error flows of 7% in row and 2% in phase. And as you can see, these models, well, there's some agreement here, but there's no agreement, particularly here, where the Nacp is. And this is the Nacp in the TE mode, and it has no correlative in the TM as we wouldn't expect, right? And this is a misfit. Whoops. Just a minute. Here's the misfit of the data. TE average misfit of 2, TM average misfit of 2.7. And what I really encourage you to do is always to look at the misfits, right? And you can see that there's one particular site here that I should take out, otherwise TM fits really well. And TE, it doesn't have spatially consistent misfits. It's kind of random, which is another good thing. So let's now do a joint inversion. And what I want to impress on you is that this is a true joint inversion, in as much as the TE and the TM mode see the Earth very differently. Maxwell's equations are decoupled, and so we're actually doing a proper joint inversion here. And on the top, you have the joint inversion. On the bottom left is the TE, bottom right is the TM. And you can see that the joint inversion, and what you do is actually you're kind of moving between these two, right? This is what are you gonna move more toward the TE side or move more towards the TM side? But here we have the model, and the NACP has been well imaged in this inversion. But when we have a look at the misfits, again, we've got this horrible misfit because of this site I should have taken out. We have now correlative misfits, as you can see. So the TM mode is saying, wait, there's number of sites, number of frequencies that are poorly fitting the data. So now we'll do a joint anisotropic inversion. And when you're doing an anisotropic inversion, you have another regularization factor, tau anisotropy, and its choice is critical. Just like the normal regularization, smoothness regularization choice is critical. The anisotropy tau choice is critical, and I can move around with that. And this is the tau that I eventually chose. And here you can see that we've got a very good fit, actually, 1.5. And the anomalies now are consistent. Here's the NACP anomaly. And the misfits to this model are much better than they were previously. So for the crustal story, the NACP is intimately associated with the Trans-Hudson Orogen. It lies in the west or north of the internide of the internal part of the Orogen. It's got significant along strike response, but virtually no across strike response. This is likely due to highly anisotropic conductors on echelon imbricated metasediments. Where exposed, we can associate the NACP with sulfides, pyrite grains in fold hinges. Now, Bedrosian and Finn, and previously, of course, Camfield had suggested that a different interpretation in terms of graphite, but there's no evidence in the Larange belt for this. What we have evidence for are pyrites. Along strike continuity and similarity to the NACP suggests continental scale orogenic processes. So that's the crustal story. It's a lovely story. But what was going on with these very long periods? Just to remind you, something that Camfield and Gough found in the early 70s, they found a very strong current concentration at very long periods, 12 hours periods. That crustal anomaly that we've just been talking about will not give you that response at very long periods. And so it's important that we give an explanation for this too. And so I re-looked at the data along this whole profile, and I went to as long a periods as I could, and I found a bright conductor in the lithosphere that I'm calling anomaly G. So here B, this is the NACP that we've been tracking all the way around, associated with LRB, the Larange belt. So we know all about this. We spent a lot of time on this, but when we focus on the long periods along this lithoprobe profile, we find an anomaly underneath this whole domain of a conducting structure in the mid-lithosphere. What the heck is that? So the only other evidence, information we have actually is from a tomographic study and from kimberlites. And on the left here is a tomographic study conducted by Bank, Bostock, and Ellis. And these red blobs show low velocity zones. And on the right are the locations of three major kimberlite fields. This one called F. Fort Alacorn is the largest kimberlite in the world. And two other kimberlites, Sturgeon Lake and Candle Lake. And as you can see, these lie along strike. Here's my anomaly G. as I showed you before, this anomaly G, it lies right here, exactly where we have this low velocity zone, and a long strike from where these kimberlite fields are. So this mantle conductor G lies directly beneath the crustal expression of the NACP. It correlates with the low velocity zone. It's a long strike from major kimberlite fields. It's correlative with exactly what I saw in the slave craton. Here on the bottom right is an image of the conductor, the central slave mantle conductor in the slave craton. And you had kimberlites at the Lac de Gras kimberlite, LDG, huge amount of kimberlites. And you have low velocity zones associated and anisotropy associated, seismic anisotropy, and you have a conductor here. So these things look very, very similar. They also look something like the fingers of God, what the Australians have been looking at. So are we looking at pathways of fluids here? So is in fact the NACP, is it due to metamorphic tectonic interpretation of Archean age, or is it due to something that the kimberlites have brought in of Cretaceous age? And you've got these fluids coming up, COH fluids. So the conclusions to the mantle story is that the NACP has got a deep lithospheric mantle expression that spatially correlates with the surface expression of the internides of the Trans-Hudson Orogen. One interpretation is that processes that occurred 1.85 billion years ago have left a geophysical marker, high conductivity, low velocity in the lithospheric mantle that can be imaged today. The alternative explanation is that this anomaly G is not old, but it's new. That it's a consequence of kimberlite magmas leaving a residue from COH fluids during magma ascent. And so I don't know how we can decide between these two. And I had the same problem in the slave craton. So I think this is an excellent example of mineral system mapping. We've mapped this wonderful NACP, and so we know we can target now. We can tell people where to go to open minerals. I don't think the story is over. I think there's a lot more that could be done. I mean, it is a big story already, but we don't understand everything. We need to understand conductivity anomaly formation in the crust and lithospheric mantle. So thank you. I'd like to acknowledge all my colleagues have been along this journey with me to understand the NACP and its relation, and particularly from MT, Juanjo Ledo, Ian Ferguson, Jim Craven, Chevy Garcia, Shane Evans, and John Booker. And I'd also like to acknowledge the giants on whose shoulders I have starred, and that is basically Rosemary Hutton, my PhD supervisor from way back, and Ian Gough and Adrian Camfield. So thank you very much for attending, and I'll take any questions from you now that you might have. Oh, Syed, hi. And I thought I could rely on Syed to give us a question. Thank you. Thanks for your very interesting talk. How can you validate your results? It can be claimed that the tau you have chosen is just to verify your story. Yeah, good point. How can you be sure that the high phases are not due to the presence of an L-shaped deep 3D structures or a suture zone? Your models were 1D and 2D. Have you studied the skewness too? And does seismic data verify the NACP is cut in the middle? Okay, a load of questions there, Syed. How can you validate your results? It can be claimed that the tau you've chosen is just to verify your story. Yeah, no, I didn't really. I hope I'm not biased like that. I know that we do have to worry about confirmation bias whenever we do any scientific work, right? And I try not to have confirmation bias, you know, and I think any anisotropic tau would have given the results that I gave. I did try a few different ones. That particular tau was the one that gave me the lowest RMS, and so that's the one I chose. So it wasn't based on the end results, it was based on how the inversion ran. How can you be sure the high phases are not due to the presence of an L-shaped deep 3D structures? Well, I think I've shown you the elongation, certainly of the airborne EM structures that are seen in the Lagrange domain. I've shown you elongation of exposed rock of the Lagrange domain. I've shown you continuity of the same type of behavior. And so I don't know how we could do, maybe somebody should do, I know Paul's got his hand up, and I'm going to let him talk in a minute. Yeah, Paul's done 3D work, but even Paul's 3D story looks very much like the 2D story, right? Have you studied the skewness? I don't really need to study the skewness. The 3D markers of those data are all very low. That distortion fit was very good to the data. Certainly on the Williston Basin, there's absolutely no 3D markers. The diagonal terms are tiny. And so there's no 3D markers in the data that would warrant 3D interpretation. And the deep seismic data to verify the NHCP is cut in the middle. No, I mean, yeah. When you say deep seismic data, I presume you're talking about tomographic data. No. Well, I guess the only thing is this, that they do get these blobs. So they whatever is causing this low velocity zone isn't continuous, although it may be just the contour interval that they're contouring things at. You do see some continuity, and you do see a break here at 52 degrees, which is about where our break was. So yeah, they do see a break in the conductor. So Paul has a question. I'll just read the question out, and I'll allow Paul to talk. You should be able to talk now, Paul.
Yeah, thanks, Alan, first for a really nice historical overview. A lot of interesting pieces in there that I had not heard. I guess I maybe have, first one question, what I put into the chat here, in terms of that deeper conductor that's in the mantle, that is something that shows up in kind of the 3D models we've been doing kind of all the way through to the southern extent near the Black Hills. And I guess I'm just curious if a plausible explanation here may be that you're looking at just more conductive Proterozoic lithosphere sort of wedged between the sort of cold, dry, refractory lithosphere on the west of the Wyoming and Hearne cratons, and on the east of the Superior craton.
Yeah, I'm sorry. I'm trying to think whether that works for other locations where we have these conducting anomalies as well, like the Slave Craton and Western Superior. I think geology in the Proterozoic was pretty similar across the globe, and so what I'd like to see are explanations that are similar across the globe. And as I said, your interpretation would give us a Proterozoic age to the anomaly. There is this possibility, though, that it's not Proterozoic in age, that in fact it is much younger, Cretaceous in age. And one reason I think that is that if you can look at these two anomalies that I have up here, both of them start at around 80 kilometers. Both the one under in Saskatchewan and the one in the Slave. And there's another one in Western Superior. It starts at around 80, 90 kilometers. And that is about the depth where we will get continuity along grain boundaries because of the wetting angle. If you go at shallower pressures than 80 kilometers, you don't get dihedral angle wetting. And so this kind of drove my interpretation that you had CO2, COH fluids precipitating, and they're connected below 80 kilometers, but disconnected above 80 kilometers. The only problem with invoking COH fluids, of course, is that you cannot have them below about 150, 160 kilometers because you've passed the graphite diamond stability field, and any carbon's going to be as diamonds, not as conducting graphite. It's going to be as very resistive diamond. Sorry, Paul, did that answer?
Yeah, I mean, I think perhaps the question I have with it being, say, something as you're potentially younger, much younger Cretaceous, is we don't necessarily have the evidence. We have this mantle conductor, going clear down for 1,000 kilometers all the way to the Black Hills, and we don't necessarily have the evidence for sort of some of these younger mantle-derived features there. But we're also, as you noted, once you get south of the border, you're buried beneath the Williston Basin.
Yeah, exactly.
There's extremely few.
Yeah.
There's very little outcrop. I guess the one other maybe just
sorry, if I can just jump in, Paul, what do you know about the southern end of the Nacp? Because there is some outcrop there, right, in Black Hills and south. Are there any kimberlites around there?
The closest thing is the state line kimberlite district, but it is actually considerably south of the Cheyenne Belt. So it's actually in kind of Yavapai age crust. So it's somewhat distinct.
Okay.
I mean, there are things like, Cretaceous intrusions, carbonatites, et cetera, further off to the east, but it's pretty much well out of this region.
Yeah. Okay.
If I can maybe just add one other thing. I mean, I don't think, you've kind of maybe set it up a little bit as sort of sulfides as perhaps the explanation or a primary explanation for the Nacp in the north, while I've kind of gone the graphite route. But I really don't think these are mutually exclusive. And I guess the point I just want to make is that we're looking at different levels of the system in the north and south.
Yes.
And while you're looking at an area where you're kind of at green schist species, relatively, undeformed, lightly metamorphosed, by the time you get in the south, you're down into granulite facies rocks. Right. So these same sort of reducing COH bearing or carbon bearing sediments, passive margin sediments, et cetera, are quite typically sulfide rich. So I guess I don't view that these are mutually exclusive, but I'll shut up. Thanks, Alan.
I had to laugh because we were at an EM workshop about 20 years ago, and there was a session on the lower crustal conductor. Everyone was trying to understand the lower crustal conductor. And there was a discussion about whether it's graphite or fluid. And Leonid Vanyan, who was a lovely, lovely man, unfortunately, he's not with us anymore, but Leonid Vanyan stood up and said, in Russia, lower conductor is fluids. Anywhere else in the world, it can be something else, but in Russia, it's fluids. So in Canada, the Nacp is sulfides. In the US, you can have graphite. Okay, Syed has got a follow-up question. Orogeny itself does not necessarily create conductive zones. Well, that's entirely true. It depends what sediments are in the orogeny. And in fact, older orogenies, Paleoproterozoic, probably didn't have as much conductive material around. Anything in the mid-Archean and young and older than that, if you had anything equivalent to what we have as orogenies today. I mean, we've got evidence of that in the Slave Craton, where we have collision in early Archean, and there's no conductive material in the crust at all. So entirely right, Syed. I would say that's true of the Archean, but I would say modern orogens have a lot of sediments in, have a lot of conductive material in, and whether it's sulfides or graphite, so you're generally going to get a conductor associated with orogeny. Pyrite mineralization usually occurs in tension faults. However, the faults you're showing are compressive faults. Well, I've just showed you down at the SEM scale that we have pyrite mineralization in these compressive faults. Okay, so we have laboratory evidence for this pyrite mineralization. Okay, I think there's no more questions, and I've kept you a little longer than the hour, so I'll just finish off with reminding you that next week we're going to do a little bit of a jump, and we're going to move into the sea. And Steve Constable will be talking about marine electromagnetic methods, beginnings to today. He'll give us an overview of marine EM. So this will be 1800 UT in a week's time, and I hope to see everybody there. So thanks everybody for attending, and bye, and see you next week. This video will be available quite shortly, as will the presentation. Thanks very much. Bye for now.